Okay, Organic Chemistry 2330. We're going to continue on with Chapter 12. This is Section 4. And we're going to talk about keto-enol-tautomerism. Okay, so what keto-enol-tautomerism is the fact that ketones in the presence of acids or bases can undergo a form transformation going from the stable ketone form to an alcohol alkene form and go back and forth. Now, most of the time, the ketone form is the predominant because it's the most stable. But we do know this does happen and it can be useful in its reactivity, okay? So the way this works and with acids or bases is the idea that you can go through a couple different steps. Here I'm going to show you the mechanism for the acid catalyzed conversion from the keto form to the enol form. So the first thing we have happen is a lone pair from the oxygen interacts with the acid of the proton of an acid, generating a protonated carbonyl compound here. Now, this conjugate base of the acid that was used can now act as a base and pull a hydrogen off of this carbon here, regenerating our acid and giving us our alcohol form and our alkene here, and regenerating our acid. So this is going constantly back and forth, back and forth, back and forth. And most of the time, this is the more stable form. However, the fact that we can form this in even small amounts in there is evidence in the reactivity we generate from these systems. One of the evidences we have that this happens on a regular basis with even trace acids or bases is the fact if we start with an enantiomerically pure or a chiral carbon on one side of our ketone here, and we place a drop of acid or base in the system, after a little while, what's going to happen is it's going to go to this enol form. And when that enol form reprotonates, gives us back our ketone, it can go to the other isomer because there's nothing, because it's going through this trigonal planar thing, and the proton can come in at the top or bottom, meaning that we can get the half R and half S each time it goes. And so then it's going to go back and forth to this enol and back to this other system. So even one drop of acid in a few minutes is all it takes to go through this achiral enol to the two different forms of it, R and S. Therefore, it is going to racemize the system or make a racemic mixture of R and S of the ketone. Okay, so there's another way to use this, our advantage, is the fact that we can have that reactivity of the alkene do work for us by creating a new functionality. So one of the things we can do is what's called alpha-halogenation. So what we want to do is we want to actually halogenate this carbon that is one carbon over from the carbonyl or the alpha carbon. And so what we can do is using that keto-tautomerization, we can make the reactivity of this group here such that we can actually add that bromine to it. Okay, so the mechanism we have for that is, first of all, we have to undergo that keto-tautomerization form. Remember, the ketone form is the more stable and it usually shows here. But once we form this enol, the alkene can then interact with that nonpolar bromine-bromine bond to generate our protonated intermediate species here. Now, our bromide ion here can act as a base and pull that proton off and give us back our brominated ketone. Okay, so if it gives us back our brominated ketone, our alpha bromo ketone here, we can then do further reactions on that by displacing this bromide in any of the other substitution reactions. We can use any nucleophile to displace this bromide here because it's a good leaving group. And we can generate new compounds like this amino compound, where it's this alpha amino ketone compound, because we took advantage of the fact that we had that enol keto-tautomerization going back and forth to give us our bromine here. And once we have our bromine there, we can displace that through a regular SN1 type reaction to give us a new chemical compound.